Hi everyone, this is Kalyan Kumar this side and welcome back to Chemistry Universe. In today's video, we're going to start the lesson Electrophilic Aromatic Substitution. And this is part 1 of that. And in this one, we will talk about basic introduction and general mechanism as well as kinetics of electrophilic aromatic substitution. Now let me begin by saying that generally this particular lesson belongs to the chapter hydrocarbons. We've done alkanes, alkenes, alkynes, and this particular chapter is named as aromatic hydrocarbons. Though we call it electrophilic aromatic substitution because we are not going to be interested in finding out methods of preparation of these aromatic hydrocarbons. Rather, we are interested in a particular reaction of these hydrocarbons. And this particular reaction that we are going to talk about is called the electrophilic aromatic substitution, which is why it's named like that. But it does form the part of aromatic hydrocarbons. So let's start with the video, and this is part 1, introduction, general mechanism as well as kinetics of electrophilic aromatic substitution. Alright, so let's begin and let's understand what this is. To the introduction. Now, aromatic hydrocarbons are known generally as arenes. An aryl group is the one that is derived from an arene by the removal of a hydrogen atom and is represented by the symbol Ar. Thus, arenes are designated as ARH, just like alkanes are designated as RH. So I think it's pretty easy to understand this. So if I have, let's say, methane, I can write it as CH3H, and this is called a methyl group. So when a methyl group is attached to a hydrogen, we call it methane. Similarly, an aromatic hydrocarbon would be an aryl group attached to an H, and this particular one is called benzene. So this part is the aryl group. And if it is only the benzene part, then we call it the phenyl group. But in general, it is known as AR. So ARH would be an aryl hydrocarbon, just like RH is an aliphatic hydrocarbon. Now, the electrophilic aromatic substitution is a substitution reaction by an electrophile on aromatic compounds. Now, here we need to understand this, that when we say electrophilic aromatic substitution, let's understand what this basically means. Now, electrophilic, you definitely understand. It's an electrophile, an electron deficient species. And we say electrophilic aromatic, obviously happening on an aromatic ring. Substitution. Now, substitution means that something comes and a similar species goes out. Please understand, substitution is not that something comes and something goes. Something comes as an electrophile and something goes as an electrophile. Something comes as a nucleophile and something goes as a nucleophile. Just as we saw in the case of alkyl halides, we talked about nucleophilic substitution, where a nucleophile came and a nucleophile went. Here we are talking about aromatic substitution, where an electrophile comes and an electrophile leaves. So basically, we have benzene attached to EB. Is attacked by EB, and E is the electrophile, B is the base. So one of the hydrogens of benzene goes away and the electrophile sits in its place, and the hydrogen then goes with B and forms HB. Now, another very important thing is that benzene shows only electrophilic substitution. All aromatic rings, other than of course hydrogenation and stuff like that, but when it comes to substitution, they only show electrophilic substitution. Benzene does not show nucleophilic substitution. And there are a variety of reasons which you are about to find out. So benzene shows only electrophilic substitution and not nucleophilic. This is because benzene is electron rich, pi electron cloud, and would repel a nucleophile. It would in fact attract an electrophile. And the second reason is there is no good leaving group in benzene for a nucleophilic substitution reaction. Hydrogen cannot leave as H- as it is an electropositive element. It can, however, leave as H+. So it's pretty simple to understand. Why does it show only electrophilic? Two reasons. One, being electron rich, pi electron cloud above and below the plane of the benzene ring. So this pi electron cloud would make benzene electron rich, make it behave as a nucleophile. So what would it attract? Obviously an electrophile. So that is the reason why electrophiles comes and nucleophiles don't come. The second reason is that if the electrophile comes, there has to be something in benzene that can go as an electrophile, because as I said, substitution implies electrophile coming in, electrophile going in, nucleophile coming in, nucleophile going in. So whenever something comes and something goes, they have to be similar species. So if an electrophile comes, the hydrogen of benzene can go as H+. You know that H+ is easily formed. All acids give H+. So H+ is easy to form because it is an electropositive element. But H- on the other hand is very, very difficult to get. There are only a very few species which can give H-, mostly metal hydrides. And therefore, you will not find a nucleophile coming in and benzene losing an H- to give away the H- and get the nucleophile. So that is the second reason why aromatic rings, especially benzene, is not going to show nucleophilic substitution. Alright, so let's look at the general reaction mechanism. Now, electrophilic substitution in benzene ring is believed to be a bimolecular SE2, which involves the following pathway. Now, S, remember, stands for substitution. This is substitution. This E stands for electrophile, electrophilic rather. And this 2 stands for bimolecular. And this is how the reaction happens. Now I'm showing you a step called step 0. Now generally, as I said, it's a bimolecular reaction. Of course, that does not tell you how many steps are there. Generally, in electrophilic substitution reactions, you're only shown 2 steps. I'm going to show 3 steps. But since majorly it is those 2 steps which are the important and key steps, the third step that I'm going to show, which I'm going to call as step 0. Step 0 is the step where the electrophile gets formed. Now you may wonder, why are we bothered about why electrophile is formed? That you'll realize as we do more and more reactions. But it is very vital to understand that electrophile formation is also an important step, because many times you'll be asked which of the following reagents would form a particular compound using electrophilic substitution. For that to happen, you need to understand how the electrophile is formed in the first place, which is why I'm going to show you step 0. So here, of course, if I take EB, it's pretty simple. It is going to give you E plus and B minus. But in most of the cases, you will not find something like an EB giving E plus and B minus. In this case, of course, step 0 is not that important. As the electrophile comes closer to the benzene nucleus, a pi complex is formed, which rearranges to a sigma complex. So this is what happens. You have step 1 and the electrophile comes closer, and as it comes closer, it gets attracted to the pi electrons of benzene. That is called a pi complex. Now that pi complex, as the electrophile comes closer, let's assume that by chance it comes closer to this carbon atom. So what would it do? It would tend to pull electrons from this carbon atom. Now this carbon atom is connected to this carbon atom by a pi bond. So as the electrophile tries to pull electrons from this carbon, the electrons of the pi bond move towards that carbon to which the electrophile has come closer to, and then this attacks the E plus, giving you what is known as a sigma complex here. So, and this will undergo resonance, and typically you will have 3 resonating structures, and the actual one would obviously the hybrid. This would be the hybrid. So this is step 1. Electrophile coming in, forming a pi complex initially, it's getting attracted to the pi electrons, and then forming a sigma complex by the breakage of a pi bond. Now, in the next step, the proton is lost by the rhenium ion, which is accepted by the base. By the way, this intermediate is called an rhenium ion. I'll just show you what other names it has. So this is the sigma complex. The proton leaves, which is captured then by B minus, and this is called the rhenium ion. This intermediate is known as rhenium ion. You can call it sigma complex. You can call it Weyland intermediate, and you can even call it cyclohexadienyl carbocation. Now the B minus takes the proton, and voila, you get the electrophile setting on benzene, and the hydrogen has gone to B. Now here we are going to find out what is the rate determining step. Now before I do that, please understand my question. If you look at the screen, you'll notice the question is rate determining step or the slow step can be found out in the following ways. Now what do you mean by that? You see, many of you are going to look at the two reactions and theoretically try to find out which is the rate determining step, right? You'll say, okay, this is the rate determining step because of this reason. And this is going to be a fast step because of this reason. My question is not which is the RDS right now. My question is, how do you find out? And not using theoretical knowledge or theoretical logic, but by experiment. Because remember, science basically is an experimental science. Okay, science is basically experimental. So what we do in science is we do an experiment, we get a result, and then we put forward a theory to explain that. And if it works in multiple cases, we say, okay, the theory is working. So how do we find the RDS practically? By experiment. How do you do that? You obviously can't take a stopwatch and say, okay, the first step is happening, okay, it's just happened. The second step is happening, now it's happened, and I calculate the time. You can't do that because you don't see those two steps happening. You just see the reactant and you see the product. Those two steps have happened in between. So for you, it's a simple reaction. Somehow we are able to get the mechanism. We are not going into that part. But once that we know what the mechanism is, let's first of all find out experimentally which is the RDS, and then we can put forward all the logic and all the theory and everything. So I want you to pause the video now, and I want you to find out, think about how would you go about finding the RDS, and then of course we would use logic. Don't go the other way around. Don't see the logic first and then try to think of an experiment. I mean, even if you do that, it's okay. But preferably, try to think of an experiment that can help us figure out the RDS, and then we will explain why it is the RDS. And remember, what is RDS? Rate determining step. It is the slowest step of the reaction, which determines the rate of the overall reaction. And of course, in these cases, we're going to assume only one reaction is the RDS. So pause now and think about it, and then play it back. All right. So what we do, one of the ways of doing that is you change the electrophile and don't change the base. So what I'm saying is, instead of EB, take maybe GB, some other electrophile, base remaining same. So if the electrophile is changed, which step do you think is affected? It is the first step which is affected, because it is the first step in which the electrophile is attracted to benzene and forms a bond with benzene. So in one case you have a E plus, in the other case you have a G plus. Obviously, since they are different, their reactivities will be different. So by changing the electrophile and keeping the base same and keeping the aromatic system same, if I notice a change in the reaction, it implies first step is the RDS. But if I don't see any change in the rate of the reaction significantly, I'll say, okay, it is not the first, it is the second one, which is the RDS. So change the electrophile, keeping the base same. If the rate changes, then it is the first step, which is the slow step, because the electrophile reacts only in the first step. And needless to say, I time and again tell you this, make notes while watching these videos. See it as a class. Don't get interrupted during the class. Make sure your focus is completely on what I'm talking about and what I'm showing. Make notes just as you would in an actual physical classroom in front of a teacher. That is the only way you'll be able to learn perfectly. So sometime what I will do is I will be talking about something on a slide and I would be wanting to refer to the previous slide, and I may not show you the previous slide at that moment, but you must consult your notes. Since you're already writing it, you should immediately go back to that part of your note and then be able to understand what I'm talking about. All right. The second is how about changing the base? Suppose I have EB and I have EL perhaps. So electrophile is the same, but the base is different. Now, in which step does the base actually participate? Second step. So in second step it participates, it implies that the change in the base would affect the rate only if the second is the slow step. So change the base keeping the electrophile same. If the rate changes, then it is the second step which is the slow step, because the base reacts only in the second step. Now can you figure out two more methods? Well, there is one. What we do is we take benzene and do the reaction by an electrophile and a base, EB, and we get the rate. In the next instance, we do the same reaction with EB, but instead of benzene, we take hexadeuterobenzene. That means we take, instead of C6H6, we take C6D6. Now, in which step does the CH bond break? Look at the mechanism. It is the second step. First step is only the electrophile attracting to the benzene ring, attaching to the benzene ring. So, if I take C6D6, the only difference this particular compound will have is on the second step. So, if the second step is the slow step, then C6D6 would show a substantial change in rate of the reaction with the same EB compared to benzene. But if the step 1 is slow step, C6D6 is going to react almost with the same rate as a normal benzene does. If the reaction were carried out with hexadeuterobenzene with the same set of electrophile and base, a change in the rate would be noticed if the second step was a slow step, primary kinetic isotopic effect. All right, can you think of one more way? Well, there is one more way. I take benzene, I take benzene with hydrogen, and I take EB, I do the reaction, measure the rate. Now I put a group on benzene, and the group to be releasing or withdrawing, and then I do the reaction with the same EB. Now, if it is a releasing group, let's say, it's going to make benzene more electron rich. So, in which step would the electron richness of benzene affect the reaction more? It will be the first step. Why? It is in that step that benzene is capturing the electrophile. Don't you think if benzene is more electron rich by the presence of a releasing group, its ability to attract the E plus will be greater? So by putting a releasing group, if I am able to increase the rate of the reaction, first step is a slow step, but I don't find any change in the rate of the reaction, second step is the slow step. Second step would be the first step. So if I put an electron releasing group on benzene and I find a change in the rate, now which step is it affecting? It is affecting the first step, because it is the first step that this particular electron releasing group on benzene is making benzene electron rich enough to be able to attract the electrophile. So by putting an electron releasing group, if the rate becomes faster, first step is a slow step. And if the rate doesn't change, obviously, again, first step is a slow step. But if I find that the putting of a releasing group, or for that matter, a withdrawing group, doesn't change the rate of the reaction at all, Meaning making benzene electron rich or poor is not going to affect the rate of the reaction. Obviously, first step is not the slow step. If an electron releasing group were introduced on the benzene ring and then we carry out EAS, we will note an increase in the rate if first step is slow, or else the rate would decrease if second step was slow. This is because an electron releasing group would stabilize the intermediate and speed up the first step and slow down the second step since the reactant is destabilized. So in the first step, the intermediate is a carbocation. Carbocation will be stabilized by releasing groups. And if the product of a step is stabilized, the reaction goes faster. And in the first step, carbocation is the product. In the second step, however, the carbocation is the reactant. So if I put a releasing group, it will stabilize it, making the reaction in fact slower. Okay, so these are some of the ways by which we'll be able to practically, experimentally find out which is a slow step. So now comes the $1 million question, which is the slow step? So I want you to look at the two steps, find out which is the slow step and figure out why. Well, it is the first step, which is the slow step, as benzene is losing its aromatic character in it. The second step would be very fast as the intermediate is gaining the aromatic character. Now, the next question that comes up is, okay, H plus was removed by E plus, right? E plus came, H plus went. That was the overall reaction. The question is, why doesn't the other way around happen? Why doesn't H plus come and E plus leave? What makes E plus remove H plus? After all, both are plus. If E plus can remove H plus, why can't H plus remove E plus? Why can't the reverse happen? So that is a question that we need to answer. So can H plus replace E plus from the product? Can the reaction go reverse? Well, if the E plus is more electrophilic, that means more electron deficient than H plus, only then the reaction occurs. That is why it goes forward. However, the reaction can remain in equilibrium with the product in cases where the electrophilic nature of E plus and H plus are very close, sulfonation and iodination. This we'll talk, of course, later on, but it makes sense. If E plus is more electrophilic for some reason, maybe E is a highly electronegative element, and the plus on an electronegative element is not stable, so it reacts faster. Whereas H is relatively an electropositive element, so the plus on it is stabilized, so it will not react that much. So unless and until E plus is more reactive than H plus, it won't be able to replace it. And if the reactivities are comparable for some reason, then yes, the reaction can remain in equilibrium. Why doesn't the base attack the carbocation in the second step? The base is negatively charged and the carbon is positively charged. Why does it attack the H and remove it? The H doesn't have a positive charge. Now let me just show you what I mean by this. Let's look at this. Now this is what I'm trying to say. Why does B minus not directly attack the plus? Shouldn't the minus attack the plus directly? Rather than taking the H and then this bond going and forming this? Can you figure out why it is not happening that way? Well, I think it's pretty simple. This is the only way this intermediate can regain the aromatic character. So, by attacking the H plus and removing it, the intermediate becomes aromatic. It is not that the base knows this, all reactions happen and the one leading to the most stable product is most irreversible. It's not that the base knows that I need to take the H plus. The intermediate itself wants to give the H plus because it wants to become aromatic. So it's readily handing over the H plus to the B minus, which also makes you understand this, that B minus doesn't have to be a strong base, because the intermediate is readily handing over the H plus to B minus and say, take it away, I want to become aromatic. And B minus is then taking the H plus. So it is the gain in aromaticity that is making it. Of course, the molecules don't know it. There may be a few molecules in which B minus may have attached directly to the carbocation formed. But in majority of cases, it will take the H plus because the product is aromatic, number one. Number two, it also implies B minus need not be strong. It can even be a weak base. So let's finally look at the kinetics of EAS. Well, this is the way it shows. This is the reaction coordinate and this is the free energy. And it goes like this. Okay, now let's understand what this is. The first one on this part is obviously the reactant. What is the reactant? The reactant is benzene and EB. So what is the transition state? What has happened? The E plus comes close to the benzene and forms a pi complex. A pi complex because the aromatic character is still there. But then it removes the pi bond and directly attaches to the carbon with a sigma bond properly, and the plus comes entirely on the carbon. This is the sigma complex. Now remember, H plus is leaving. As H plus leaves, the CH bond becomes weaker and weaker and weaker. The pi bond starts getting retained on the benzene ring, and you again get a pi complex. But here, it is the H which is having the delta plus. And then eventually, H completely leaves and you get the product. And if you notice, this TS is higher than this TS simply because the plus on H is more stable than the plus on E, which is why E is a more reactive electrophile. The very reason this reaction is happening, remember, is because electrophile is more reactive than H. And therefore, E delta plus will be less stable and more energetic than H delta plus. So of the two TS, the second one is more stable as the H has partial positive charge because the partial positive is less stable on the electrophile since it is more reactive. And that ends the part 1 of this particular video. So I hope you were able to understand the introduction to electrophilic aromatic substitution. It's a very simple reaction. The next part is going to be pretty longish. It's going to be very long because we're going to discuss all the electrophilic aromatic substitution reactions on benzene, of course. So that's going to be a pretty long one. And again, whenever you watch a long video, try and make sure that, you can focus completely on the lesson and don't break the continuity. And if at all you do break the continuity for some reason, make sure that a particular set of reactions are over and then you take a pause and come back and see the video again. And remember, it's not seeing the video, it is making notes. This is not some YouTube video, you just look at it and enjoy or learn something simple. This is something to do with your academics. It takes time. Make notes, read them, and if you have any questions, put them in the comment section below. With that, this is Kalyan Kumar signing off. Have a wonderful and great day, and thank you for watching this.